Okay, welcome to another day of operations research. This first video this week will be sort of an overview of optimization. The goal this week is to kind of do a broad tour of different topics in optimization. And so this is kind of the overview video. So let's start off with a tour of optimization problems and kind of talk about some of the different types of optimization problems that you might run into and kind of order them from maybe easiest to most difficult. And so we've spent a lot of time so far talking about linear optimization or linear programming. This is the case when both our objective and all of our constraints are linear. And we know a lot about how the simplex method works and how to kind of formulate things in terms of linear programming. The next stage up, and I'll have another video talking more specifically about this, is quadratic programming. Okay, in a quadratic program, instead of having a linear objective, we'll have a quadratic objective. Depending on kind of the flavor of quadratic programming, you often still have linear constraints, but there's variations of quadratic programming with quadratic constraints as well. And so what does a quadratic constraint look like? Well, maybe let's talk about a linear constraint or a linear objective. Looks like sum of maybe ci xi, and we want to maximize this quantity where c is some costs or weights or coefficients, and xi's are our decision variables. Quadratic programming, we're going to look at objectives with quadratic terms, meaning that there's multiplication between decision variables and also squares of the decision variables. And so oftentimes you'll sum over both I and j, both going from 1 to n. We'll write our coefficients as qij and then xi times xj. Okay. In matrix vector form, this is often written as the x vector transpose times a matrix of all of these q coefficients times the x vector again. And so this is sort of row vector times matrix times column vector ends up giving you just a number. So this is a 1 by n times an n by n times an n by 1 gives you a 1 by 1. And so that will just give you a number. And so whereas on the other hand, this usually looks like C transpose X, where our C is our vector of coefficients and our X is our vector of decision variables. And so, for example, you might have sort of Q11 X1 times X1, so X1 squared, plus Q12 X1 times X2, plus ... And so quadratic objectives will include some of your decision variables squared, as well as products between your decision variables. Okay, and in general, quadratic programming will have maybe a quadratic term plus a linear term in the objective. And so you'll have sort of both a quadratic and a linear term possibly in your quadratic programming objective. Okay. Nice thing about quadratic programming is that you can actually solve them based off of very similar techniques and variations on how linear programs are solved, depending a little bit on kind of the properties of this Q matrix and whether it's positive semi-indefinite or not. But we won't go that deep into it. And so that's quadratic programming. The next kind of challenge beyond that is what's called convex optimization. And if you have a general objective function, so both of these we sort of assumed a specific form to our objective function, either that it was linear or quadratic. But if you have just an objective function where you want to either minimize or maximize some function of your decision variables, you hope it's a convex function. Okay, and so what's a convex function? A convex function is one that in 1D, maybe it's easiest to see it in 1D, is kind of well, maybe concave up. But the important thing about a convex function is if you take any 2 points and connect those 2 points, the function is always beneath the line or plane or hyperplane connecting those points. And so when you have this property of convexity, both for your function as well as your domain. So we also talk about a domain, so a feasible region being convex. If you take any 2 points in that region and any line connecting them stays completely inside that region. And so this would be a convex region. This would be a non-convex region because you'd have to, if you connected these 2 points, you'd leave the region. So anything that kind of dips in on itself is non-convex. So in convex optimization, you want a convex objective function as well as a convex region. And if you have those two, then some really nice things happen. The main one being in that if you find a local optimum, okay, it's going to be a global optimum. And we'll talk a little bit about the difference between local and global optimum in just a bit. So kind of here, we're kind of got an arrow here in that as we go down this list, things are getting harder in general. There's always some special cases where things that seem like they should be hard end up having sort of nice solutions. But in general, quadratic programming is harder than linear programming, and convex optimization is harder than quadratic optimization. And then the not so nice ones is then when you have to deal with what's called non-convex optimization. Okay, and I'll talk a little bit about what is the big challenge of non-convex optimization that makes it so much harder than dealing with convex optimization. Let's look at a one-dimensional objective function that's not convex. Okay, and so there, when it's non-convex, there's going to be parts where it goes up and down, and you're going to get, and let's say this was our function f of x, and we wanted to minimize it. Well, we noticed that there's going to be several different points that are what are called local minimum. That's going to be what we call a local min. And these local min are going to be lower than all the points nearby them. And that's going to be tricky because if you're testing that point and you're only using local information about kind of looking at nearby values of the objective function, it's going to look like the optimum. But if you were to kind of break out of this valley and get over to this valley, you'd find an actual a better optimum, and the best one we call the global minimum. Global mean overall best, local meaning best amongst its nearby neighborhood. Okay, and in general, when you're dealing with non-convex optimization, you might have an objective function that has many of these local minimums, and it might be very hard to search the whole space to find which one is actually the global minimum. Okay, and that's going to be the difficulty with non-convex optimization. Oftentimes in non-convex optimization, you're using strategies that are trying to help you get out of local minimums and to broadly search the space. Either that or you're settling for things that are local mins and saying that's good enough. So in optimization, there's a lot of problems where we're looking for the best, but sometimes we're just looking for good enough. And sometimes that's what you have to limit yourself to when you're dealing with non-convex optimization. Okay, so this is kind of our tour of different optimization problems. There's definitely different ways we can break down and categorize different types of problems within these. But these are some broad kind of groupings. Oh, one more I had on my list. So at this point, these two are both assuming that we're dealing with continuous variables or that kind of take on any real value in between. And so maybe they might be vector valued, but they're continuous variables. The last one that I'll put here that it can be more challenging or just as challenging as non-convex optimization, though in some special cases, they end up having nice algorithms that work for them. But then I'll kind of put as a separate group, problems of combinatorial optimization. Essentially, these are often when you're looking at optimizing over a discrete set. So this is things like where we were doing integer programming, where you've got discrete values, so you can't take on all the values in between. And so these turn into sort of search algorithms. We're sort of searching for the best solution amongst the set of solutions. And although that discrete set might be finite, it might be infinite and kind of discrete, but it might be finite. It often is very, very large. And so we'll do a couple examples of some combinatorial optimization where we're searching over a discrete set, but that discrete set might be really large and it might be really, really tricky to find good solutions once the problems get even moderately sized. Because sometimes the number of possibilities grows exponentially as you add kind of just a few more items that you're searching over. Okay. So that's kind of a general tour of some different problem types. Let's do a little bit of a tour of different problem strategies. Okay, some optimization strategies. One that we've met already is linear programming. And we've spent a lot of time talking about simplex method and ways that the linear program can be solved. This can be modified to solve some related problems, but to solve quadratic programs. And if you check the book, that's covered in 13.7 on how to do that. And what are called separable programs. And that's in 13.8. And so if you check those two sections in the book, it'll provide some details on sort of how you can take linear programming and adjust it to deal with a quadratic objective function as well as a separable objective function. Okay. The next family of strategies, and this is really a whole family of strategies, there's a lot of different variations on these strategies, are what I'd call gradient-based methods. These are in general good for convex problems, especially when you have a convex problem with continuous objective function and and that's also differentiable, or you can take a derivative of. Okay, and so these ones you're usually looking at min of f of x. It might have constraints. Oftentimes, these objectives maybe don't necessarily have constraints, and it's just the objective. And so let's say f of x is our objective function. These strategies use something called the gradient. And the gradient of f, we sometimes denote with this triangle in front of the f function. That is going to be a vector of all the partial derivatives. And so you can take a derivative of f with respect to its first variable, and then a derivative of f with respect to its second variable, on down to a derivative of f with respect to the last variable. And these are what are called partial derivatives, which means you take the derivative with respect to that variable and treat all other variables as constants when you're doing that derivative. Okay. The important thing about this gradient vector that we get by creating this vector of all these derivatives is this gradient, it always points, what I'd say, uphill. So it points in the direction where f of x is increasing the fastest. Okay, and so if we want to minimize f of x, we go in the opposite direction of the gradient. If we're trying to maximize f, we go in the direction of the gradient. And so then the whole idea or the basic general strategy is that we start at some point, we'll call this x, and I'll put a little 0 in parentheses there, is that we choose a starting point. Okay, so these gradient methods, you have to tell it where you want it to start. And if you start in a different place and it's a non-convex problem, you might end up in a different optimal solution or a different local optimal solution. But you start at some spot, and then you have a recursion, so an iterative process, where in order to find your next spot, you take your previous spot and you make a small step in the opposite direction of the gradient if we're trying to minimize f of x. And we evaluate that gradient at the previous step, at the previous x. So at each step, we have our current solution, we plug it into the gradient function, and that will tell us which direction to go. And we multiply that by a small number here. Eta is what we call the step size. Okay, and we make a small step in the direction opposite of the gradient. And so visually, we can kind of maybe think of a topographic or so maybe here's our grade here's kind of a height map of our objective function. And if we start off here, the gradient's going to point downhill. Maybe here's the optimal solution. Gradient's going to point this way initially, and we're going to take a step and we're going to move forward, and then it's going to point this way, and we're going to be here, and then it's going to point this way, and then this way, and then get us to our optimal minimum solution. Okay, and if it's convex, and convex and continuous and some other nice things, then we're guaranteed that these gradient-based methods will eventually bring us to the optimal solution. So essentially, we're making small steps. Each step brings us downhill and brings us closer to the optimal solution. Okay, and these are really good for convex problems. You can use them on non-convex problems, but you're only guaranteed to get a local minimum. And so they'll get stuck in sort of a small valley when there might be a deeper valley somewhere else. Okay, so that's gradient-based methods. And then the last thing that I'll mention is what are called meta-heuristics. And these are less of a kind of specific strategy and more of a general strategy. And so these are strategies that look for what I'll call good, but maybe not best solutions. Okay, and a lot of these strategies are built to deal with non-convex optimization, and they're built around searching a broad area of the feasible region. They're flexible, kind of overarching strategies that then you can make specific to your problem. Um, And so a lot of the challenge of using these meta heuristic is deciding how are you going to implement them to solve your specific problem. Um, and so one thing I'd say is that if you want to apply one of these meta heuristics to a specific problem, look up and look for papers that maybe discuss how it's been done in the past. There's often many ways you can do it, and you can try maybe a couple different ways to see which ones give you the best results. Um, So some examples of these meta heuristics would be things like genetic algorithms, simulated annealing, um, ant swarm optimization. A lot of these meta heuristics get their kind of inspiration from biologic processes, and there's some areas of kind of mathematical optimization that really love if they can put a biologic connection on this. So things like ant swarm, of kind of gaining some inspiration from how ants find the best path, or something like that. So I'll leave you just with a rule of thumb that I'll kind of wrap up with, is that most problems have uh, algorithms that work well on them. And you're going to do better if you use the right algorithm. So there's a lot of problems that you could hit with a meta heuristic and it would give you a good solution. But there's oftentimes specific algorithms that have been tuned and tested to deal well with specific problems. And so we'll do a video this week on the traveling salesman problem. That's a really interesting combinatorial optimization problem. It's been investigated a lot. You could use different meta heuristics on it, but at this point in time, there's some very well-tuned methods for solving the traveling salesman problem. And so the rule of thumb is if there's a good algorithm, use it. And so sometimes that means looking around at the literature to find out what is that good algorithm. Ideally, hopefully you can find that somebody's implemented that and there's maybe a package available that will solve your problem. And then usually the challenge is coercing your problem to sort of fit into the structure of the associated problem. And so half the challenge oftentimes is realizing that your problem is equivalent to somebody else's problem. So that's sort of an overview and a tour of optimization, and some of the topics that we'll cover this week.